So we're talking about infinite limits. And limits at infinity. So let's do some review quickly. Infinite limits were limits that ended up giving you infinity at the end of the day, when the y value goes to infinity. So for example, I could ask you to calculate the limit, evaluate each limit. I can give you the limit as x goes to 4 from the negative of 1 over x minus 4. How do you figure out what this is? First step, if you have no clue what to do on anything, ever in this class, the first step is probably to try to plug in 4. So what happens when you plug in 4? Yeah, so you get a constant, a non-zero constant, 1. But if you plug in 4, you get 1 on top and 0 on the bottom. When you get a non-zero constant over 0, you know you're going to be looking for some sort of infinity answer. Right? When the bottom's going to 0 and the top's staying constant, you're looking for an infinite limit. But what you have to check is what happens to the left of 4, right? Since it's a negative up here. So you can do a little chart. And say, okay, here's x, here's f of x. To the left of 4 would be something like 3.9. What happens when you plug 3.9 in here?
Negative.
Negative, right? So this goes to what?
Negative infinity.
Negative. So that's kind of the simplest possible example or problem I could give you with an infinite limit. Now, let's say, make it a little more complicated. The limit as x goes to 4 again, but from the positive side this time, of x squared minus 16 over x squared minus 8x plus 16. What happens here? So what do you get when you plug in 4?
0.
Right, so if you plug in 4 for x squared, you get 16 minus 32 plus 16, which is 0. If you plug in 4 for x squared, you get 16 minus 16. So this is 0 over 0. If you ever get 0 over 0, simplify. Right, that's kind of the moral of the story here. In this case, you can simplify by factoring. So this will be the limit.
X minus 4, x plus 4.
X minus 4, x plus 4 on top.
And then x minus 4 squared.
Yeah, so this guy, two things that multiply out to 4 but add up to negative 8. Minus 4 and minus 4. So one of my x minus 4 factors cancel, but the other one remains. So I now have to evaluate the limit as x goes to 4 from the right of x plus 4 over x minus 4. What do you think?
Graph it.
Graph it, yes. What do you get when you plug in 4?
Plug in 4, you get a 0.
8 on top, 0 on bottom, right? If you just try to plug it in. Constant over 0, we know it's going to some sort of infinity probably. And we just have to figure out positive or negative. Okay, so as soon as you get a non-zero constant over 0, you're looking for an infinity. In this case, because we're coming from the right, the positive side.
4.1 positive infinity.
Yeah, try 4.1. When you plug in 4.1 on the bottom, you get positive. When you plug in 4.1 on the top, you get positive. So we know we're going to positive infinity. By the way, back on this example, what happens if I would have made it just a regular old limit without a negative? DNE, why? They go to opposite infinities from each side. I mean, if you plug in 4, you'll get 1 over 0, but when you test, if If you test 4.1 as well, the bottom will be positive, the top will be positive, so you get plus. That means you're going to different infinities, does not. Okay. What about some trig functions? We talked about those a little bit. Limit as x goes to 0 from the negative of cosecant x. How do you analyze this guy?
1 over 0.
You can think of it as 1 over sine. Right? This is the limit as x goes to 0 from the negative of 1 over sine x. And if you plug in 0 to sine, sine 0 is 0. So this is one of our infinite limit forms, right? It's a non-zero constant over 0. Then we just have to figure out whether it's positive infinity or negative infinity. You can either go to the graph of cosecant or plug in a number slightly less than 0. It's up to you. You guys know what the graph looks like?
Up, down, 0.
Yeah, so cosecant, since it's the reciprocal of sine, you'll start with a sine graph, or I would start with a sine graph. Sine starts from the origin, 0, 0, and goes like this. So cosecant's going to have an asymptote at 0 since sine has a 0. It's going to have an asymptote here, here. And then the cosecant inverts, right? So it'll go up like this, down like this. So then when we say 0 from the left side, we know we're looking at 0 from the left. So our function's going down to negative infinity. Focusing on this portion. If you didn't know the graph, you could use the unit circle approach. Basically, this comes down to 1 over sine, so you need to know for angles that are less than 0, is sine positive or negative. So on your unit circle, here's 0. If you're supposed to go less than 0, you go somewhere over here. In the fourth quadrant, sine is negative. So for angles slightly less than 0, this guy will be negative. Again, getting negative infinity. Whichever way makes more sense. Right. Two more. And then we'll go on to the other 3.5. So what about limit as x goes to pi over 2 from the positive of cosecant x? What do you think about this one?
1.
Yeah, there's no issues here. Right? You can think of this as 1 over sine x again. But when you plug in x equals pi over 2, you don't get an infinite form. Right? You don't get a non-zero constant over a 0. You don't even get 0 in the bottom at all. Right? When you plug in pi over 2 to sine, you're up here, sine is equal to 1. So this is just 1 over 1. So be careful that you don't make things too complicated. If you're not getting zeros in the denominator, then you just plug it in usually. Limit as x goes to 0 let's do from one side. Let's go from positive of x plus 2 over sine x. So what does this x plus 2 on top do or matter?
Reciprocal of that thing, the trig identity.
Right, so one idea that might pop out at you is that you could break this down into maybe x over sine x plus 2 over sine x. Right, and then do the limit of each one of these. Because this guy's that nice trig identity that we have, and he'll go to 1, right? But what's this go to? 2 over 0, which is going to go to some kind of infinity. So you're going to get 1 plus infinity, or minus infinity, which is going to be infinity again. So what I would suggest, we can do it this way, and it's not really wrong, but there's no reason not to just try to plug in 0 from the beginning here. Right? You don't get an indeterminate form if you plug in 0. What do you get?
2 over
2 over 0.
One side.
Hey, purple. Right, if you plug in 0, you get 2 on top, 0 on bottom. And then you can say, okay, non-zero constant over 0, I know this is going to go to infinity. All that it comes down to is making a little chart for, or a graph or whatever, but to figure out what happens on the positive side of 0. So in my head, I'm thinking, here's 0, the positive, an angle that's slightly more than 0 will be up in the first quadrant. Sign positive or negative in the first quadrant? Positive. Positive. Sign's positive. So this will altogether be positive infinity. This will lead you to the same conclusion, it's just making your life a little harder.
And then if it was a 2x, it would be 1/2. Instead of x plus 2,
Right here?
it's 2x.
Yes, I understand. Yes. So remember if I give you something like, this isn't technically an infinite limit, but let's think about it here. X goes to 0 of 2x over sine x. Oh. Is that what you want, or you want sine of 2x? Is this what you wanted?
Wouldn't matter, right? So it'd either be 2 or 1/2.
Right. So what's this limit?
1/2.
Yeah, so when you plug in 0, you get 0 over 0. Right? So it's an indeterminate form. But we're going to make it look like our special trig limit now. But remember, the special trig limit looks like the limit as theta goes to 0. Well, we'll do the reciprocal. But we need sine x over x or x over sine x. So actually this 2 needs to be pulled out. Right? Once we get rid of this, then it's exactly what we can work with. So this, it's 0 over 0 now. When we pull the 2 outside of the limit because it's a constant multiple, now we have the reciprocal of this quotient, and we know this limit's 1. So this overall will be 1 times 2, which is 2. 2 times 1. Right? This whole limit here is 1. So compare and contrast, if I gave you instead limit as x goes to 0 of, let's say, sine 2x over x. Yeah, so this one is the one where you have to multiply by 2, right? because the 2 is inside of the sign, so you need to match that down here. And if you multiply by 2 down here, you have to do it up here. And then this gets pulled out. So you end up with the same.
2.
Right, because you get 2 on the outside, sine 2x over 2x. This is your special limit. So this guy I actually didn't need to multiply by anything because there was no extra number in here. I don't. As soon as I pull the 2 out, these match. That's the difference. That was from what, 1.3, I think. For questions about, I guess, the infinities or the special trig limits, any questions? So the other thing we started, so this was 1.5 over here. This was old 1.3. The other thing we started was 3.5, which is about limits at infinity. So, kind of the moral of the story here is, if you plug in your number, if you try to evaluate your limit, and you get, there's kind of a couple special forms, infinity over a constant, or a constant over infinity, or infinity over infinity. So limits at infinity means you're letting x go to infinity, and so when you plug in infinity for x, you kind of land in one of these categories usually. Infinity divided by a constant is going to be infinity again. Unless, let's say it's a positive constant, right? If it's a negative constant, then it's going to be negative. Constant divided by infinity, again, if it's a positive constant, well, actually it doesn't matter here. A constant divided by infinity is going to give you what? 0, right? If the bottom gets huge, you have a constant on top, 2 over a billion, and $2 divided among a billion people, you each get $0. So constant over infinity goes to 0. Infinity over infinity is indeterminate. And we like to figure these out, the strategy is to divide by the highest power. Limit. So the limit, I'll give you 3 very similar ones. Let's see what happens here. We have the limit as x goes to infinity of 3 minus 2x over 3x cubed minus 1. The limit as x goes to infinity, 3 minus 2x over 3x minus 1. And the limit as x goes to infinity, 3 minus 2x squared over 3x. Now, you probably learned when you were dealing with horizontal asymptotes in 126 the idea of finding the ratio of the leading coefficients, and that's an algebra. I mean, that's an okay way to do it. But I'm going to try and steer you away from that. And I'm going to try to get you to put everything in one of these forms by dividing by the highest power. So what I'd like to see when you're evaluating a limit like this is for you to say x cubed is the highest power. So to try to simplify everything to one of these, I'm going to divide everything by x cubed. So you do limit as x goes to infinity, 3 minus 2x, 3x cubed minus 1. But I'm going to take everything and divide it by x cubed. Since I did it to the top and the bottom, it doesn't actually change it. And it doesn't change it. And then each of these simplify, well, some of these simplify. You have 3 over x cubed, that doesn't simplify, but this guy becomes, well, I need my limit. Can't forget that. So 3 over x cubed doesn't simplify, but 2, this will be 2 over x squared because one of the x's cancels. This will be 3. This will be 1 over x cubed. And now each of these is exactly of this form, except the 3. Right, so each one of these, when you plug in infinity, is a constant over infinity. Right, if you cube a huge number, it's still huge. So constant over infinity, constant over infinity, constant, constant over infinity. So each one of these, because they're constant over infinity, goes to 0. So what are you left with? 0 over 3, which is 0. Questions about that logic? So what would I divide by here? X. X is the highest power. All right, so you have the limit as x goes to infinity, then everything is divided by an x. So 3 minus 2x, 3x minus 1. Because the highest power, the highest exponent on any x is 1, I divide by x to the first. This guy doesn't simplify, this guy becomes -2, this guy becomes 3, this guy doesn't simplify. So because these are constant over infinity, when you try to plug in, this goes to 0, and this goes to 0, leaving you with -2/3. What are we going to do in the next one? It's infinity over infinity again, because when you plug in infinity, you get infinity on top for the x squared and infinity on bottom. So you have to try to divide by the highest power. So this becomes limit as x goes to infinity, 3 minus 2x squared, 3x minus 1. I'm going to divide everything by x squared this time. Well, some things reduce. doesn't. This does. So 3 over x squared minus 2. 3 minus 1 over x squared. Oh no, I'm sorry. 3 over x. Got to reduce correctly. There's 2 on bottom here, so there'll be 1 left on bottom. Okay, so what happens here? So you're getting negative 2 on top because this guy's going to 0. And this guy's, both of these are going to 0. So this is equal to negative 2 over 0. What's that tell you? Some kind of infinity, right? When you get 0 in the bottom, you got some kind of infinity going on. But we have to figure out whether it's positive or negative. So what I would do at this point is a little, I guess a table or just plug something in. What do you guys think it is?
Negative.
Yeah. Why?
You put in like a million for x squared to be, whatever.
Yeah, I think as x goes to infinity, you can go back to the original, maybe if it's a little easier. But as x goes to infinity, put in a big number, think, whatever, 100, 1,000, million, doesn't matter. If you put 100 on the bottom will be
300.
positive, right? 9. And if you put 100 on the top, 3 minus 2 times 100 squared, negative. So you're actually going to negative. So once you get this negative 2 over 0 or positive 2 over 0 or whatever, constant over 0, you still have to make sure you're going to the right, you get the right sign.
Would the sign of the negative 2 mean that would just be negative?
Well, kind of, no, not necessarily, because that has nothing to do with whether or not this is going to positive or negative infinity. Right?
Well, would that be like the highest code?
If this were going to negative infinity,
Highest degree.
if this were going to negative infinity, you'd have to plug in negative 100 here, right? And then the bottom would become negative. So then you'd be going to positive. Let me write that because that's a good point. If I gave you limit as x goes to negative infinity instead, 3 minus 2x squared over 3x minus 1. You do all the same simplifications, right? And you're still going to end up, you're going to divide by x squared like before, and that's still going to leave you with negative 2 over 0 when you evaluate. But then when you plug in, when you do your little table, you should plug in something going to negative infinity. Like negative 100. So if you're talking about negative 100, then when you plug negative into the bottom, you get a negative result. When you plug a negative into the top, it doesn't matter because it gets squared. So this will be 1 minus 2 times a big number. It'll be negative as well. Give you a positive. So this guy on the other side is, as x goes to negative infinity, your result is going to go to positive infinity. Once you get to this form, be rigorous about it and check a point. So now it's going to shift from the easy examples to the hard examples.
Yay.
Right? I knew that's what you were all waiting for.
The EF range.
That's right, right around EF. starts getting grown up. All right, so what if I put some fractions in the exponents? How does that make us feel? Limit as x goes to infinity of 5x to the 3 halves, divided by 4 root x plus 1. When you try to plug in here, what happens? Yeah, so the x to the 3 halves function, if you take a number and raise it to the 3 halves power, raising it to any power is going to keep going to infinity. Okay? Even square root, if you take the square root of 1,000,000, it's going to be a big number. If you do the square root of 1,000,000,000, it's going to be getting even bigger. So these guys grow without bound. So this is going to go to infinity over infinity. So it's indeterminate. So we try dividing by our highest power. What's the highest power in this case? 3 halves. What power is this one on the bottom?
Half.
Right, so what you want to recognize before you move on is that this is x to the 1 half. So when you divide everything by the highest power, 3 halves is bigger than 1 half. So you're going to take 5x to the 3 halves and divide it by x to the 3 halves. And on the bottom, you're going to divide everything by x to the 3 halves as well. But let me write this as a 1/2 exponent instead of a square root. So how do we simplify here? Well, that's easy, use cancel, right? Now on the bottom, 1/2 on top, 3 halves on bottom, what's left over?
Infinity. I mean 0. No. 1.
1 on the bottom, right? 1, if you subtract, just subtract. 3 over 2 minus 1 over 2 is 2 over 2, so there's 1 left on the bottom. Here there's here I can't simplify. So when I plug in my infinity, what happens? These guys go to 0, right? Constant over infinity. Constant over infinity. So I'm getting 5 over 0. Which is some sort of infinity, and then I would go back to my original and plug in a big number as positive infinity or negative infinity. I think it's positive, right? Because there's no minus sign in there. When you plug 100 in here, the square root of 100 cubed, some positive number, square root of 110 plus 1, so everything's positive. Let's go with the positive. What do you think? Not too bad? Except for subtracting 3 halves and 1/2.
Right?
Keep you on your toes. What about? Yeah, we want to do that. Oh, okay. So let's do some trig functions. Limit as x goes to infinity of sine x over x. What do you think? So it kind of doesn't doesn't make sense to plug in infinity, because if you try to plug in infinity to sine keeps oscillating.
Can't get bigger than
But it never gets bigger than 1. Right? So kind of the touchy-feely way to do this, the way where mathematicians would probably laugh at you, and if they watch my video, I'll probably get laughed at. This is basically, as x gets big, this is going to be kind of like 1 over infinity, plus or minus. But it doesn't matter, because any constant over infinity goes to 0. And the sign of the top doesn't even matter, because whether you go to 0 from below or 0 from above, you're still ending up at 0, right? Plus or minus 0 is the same thing. Okay, so that's the weenie way to do it, which is good. I mean, that's better than not understanding it at all. The real way to do this is with the squeeze theorem. Right? Because you know sine of x is between what? You just told me. Negative 1 and 1. That's like written in stone. So then if you divide everything by x, negative 1 over x is less than or equal to sine x over x is less than or equal to 1 over x. Then take the limit as x goes to infinity on everything. So you have the limit as x goes to infinity of negative 1 over x is less than or equal to the limit as x goes to infinity of sine x over x is less than or equal to the limit as x goes to infinity of 1 over x. And you know these are established. Right, what's 1 over x go to as x gets huge? 0, right? 1 over infinity, that's 0. And what's negative 1 over x go to as x gets huge? Still 0. So sine x over x as x goes to infinity must be 0 because it's sandwiched, squeezed between the two. Unless I specifically say use the squeeze theorem to show this is 0, you can just do this. You can just assume it's 0. But that's kind of a cheap way to do it, I guess. Oh, why isn't it 1, right? Because we've had the limit of sine x over x before and we got 1.
Because it's not going to.
Not going to 0, right? So you got to pay attention to this, where your x is headed. This is a limit at infinity. X is going to infinity. So limit as x goes to negative infinity, sine x plus x squared over cos x minus 2x cubed. So when you plug in, what's your intuition telling you here? It's going to infinity over infinity, right? Because sine is staying between 1 and 1, but this guy's blowing up. And cosine is staying between negative 1 and 1, but this guy's getting huge. And so when you have infinity over infinity, you divide by your highest power. So you're going to divide everything here by x cubed. That's my highest power. So I can't simplify sine x over x cubed, and I can't simplify cos x over x cubed. But that doesn't really matter because I'm going to use this kind of logic anyway. Just make them go to 0. These guys I can simplify. This will be 1 over x. This will be minus 2. So this guy's a constant over infinity. This guy's definitely going to 0. Sine x over infinity, since this is between -1 and 1, this is also going to 0 because the bottom's going to infinity. It's also going to 0. Luckily, this -2 is hanging out, so it's not an indeterminate form. This is 0 over -2, which is just 0. There's no arguing that. Try and argue that. I would probably stop listening very quickly. Okay, so if you have a trig function, sine or cosine over a polynomial, as x goes to infinity, this guy goes to 0. Doesn't matter if it's x cubed, x to the 5th, square root x even on the bottom, right? Sine x over square root x. As x goes to infinity, that will go to 0. Because the bottom is increasing and the top is staying between -1. Lead into a tricky one. Limit as x goes to -infinity of 5 over x minus x over 3. So when you check this and you think, what happens if I plug in infinity, what do you get? This guy goes to 0 because 5, you get a constant over infinity, or negative infinity, minus a negative infinity over a constant. So you're kind of thinking here 0 plus infinity, right? Because the minus, which is going to be infinity. Now, yeah, so you got to be careful with this kind of logic. 0 plus infinity is not going to get you in a lot of trouble. If you have a function that goes to 0, or any constant, and you have a function that goes to infinity, and you add them, you're still going to go to infinity. Right? You're just going to you're going to add a constant to infinity, it doesn't matter, it's still going to be huge. But if you get something like infinity minus infinity, then you got to be careful. Okay, infinity minus infinity is not necessarily 0. It's not necessarily infinity. Infinity minus infinity is another indeterminate form where you have to do some simplification before you can calculate the limit. So kind of the other, more rigorous way to work with this limit would be to combine these into a single fraction. So another way to look at this, to lead into the next example, would be to get a common denominator. So your common denominator is going to be 3x. This guy needs a 3. This guy needs an x. So this becomes the limit as x goes to negative infinity of 15 over 3x minus x squared over 3x. So when you combine everything, 15 minus x squared over 3x. And now this is infinity over infinity, so you can do your divide by the highest power. said, just to prepare you for the next example. But let's finish it off and make sure we get the same thing, okay? Make sure this checks out. So I'd have to bring this up, divide by the highest power, which is, looks like x squared. So this will become the limit as x goes to negative infinity. Divide everything by x squared. So this will be the limit as x goes to, calm down, Blue. Calm down, Blue. I know, you're itching to get it again. So this will be 15 over x squared minus 1 over 3 over x. So 0, 0. We're going to negative 1 over 0. So we know this is some sort of infinity. We come back and we check with our table. Since we're going to negative infinity, what kind of number are we going to plug in? A negative number, negative 100 or whatever. The top, 15 minus a positive, or when you square negative 100, you'll get some huge positive number. So 15 minus a huge positive number is negative. 3 times negative 100 is negative 300. So this is why we're going to positive infinity. So it does check. In general, if you have a constant plus infinity or a constant minus infinity, that's fine. You can say constant minus infinity is negative infinity. Constant plus infinity is infinity. But let me show you. So this is okay with me. All right? I was just doing this to check and make sure it was legit. All right? But let me show you a situation where this kind of analysis is not okay. Where you have to do something like this. Oh, thank you. Limit as x goes to infinity of x squared plus 5 over x plus 1 minus x. So what do you get intuitively when you plug it in here? Yeah, so since the top degree is bigger, you're going to get a bigger number on top than on bottom, so this will be infinity minus this will be infinity again. This is an indeterminate form. Meaning that you cannot say this is 0 or 1 or infinity. You cannot make any determination from this. So in this case, you really have to get a common denominator and then try to do something more like this. So what would your common denominator be here?
X plus 1.
Just x plus 1, right? You think of this guy over 1, so he needs an x plus 1 on top and bottom. This will be the limit as x goes to infinity. X squared plus 5 over x plus 1 minus, distribute out your x here, this will be x squared plus x over x plus 1. So what happens when you collect here? The negative has to get distributed. So this will be the limit as x goes to infinity. x squared minus x squared, the x squareds go away. 5 minus x is all you'll have left, over x plus 1. So when you divide by your highest power, this is 5 over x minus x over x over x plus 1 over x. This guy goes to 0. This guy is just 1. This guy is just 1. This guy goes to 0. So you get negative 1 over positive 1. Infinity minus infinity is another indeterminate form. You gotta simplify something. How could I make this problem end up equaling negative 2 instead?
Put 2 in front of x.
You need a little more than that. What happens if you put a 2 in front of the x here? You'll get 2x squared, so the x squareds won't cancel, so you have to put a 2 here.
You get 1 plus 1 in the
Okay. So basically, if I multiply both of these by 2, this will end up being negative 2. So I can make infinity minus infinity be anything I want. What did you say about 1 plus 1 in the denominator?
Oh, never mind. You want to take over 2?
Negative 2. Oh, you just do this. Because then you could just factor the 2 out of the limit, and it's 2 times negative 1. So you can make infinity minus infinity be anything you want. Is my point. That's why it's indeterminate. Okay. Let me give you one more set of examples, and then we'll talk about questions. Do you guys know? You guys know? You guys know what this equals? Sometimes.
Negative x.
Sometimes.
Plus minus x.
So in some cases this equals x, and in some cases it equals negative x. It equals x if you put in a positive number. It equals negative x if you put in a negative number. So what I mean is, take x equal to 6. What's the square root of 6 squared?
6.
This is the square root of 36, which we all know is 6, right? So this is when x is positive. This same kind of simplification will happen if you put in any positive x. But if you put in a negative x, like x equals negative 6, then you'll get negative 6 squared, which ends up being square root of 36 again, which is just 6. So even though you put in a negative 6, you got out the opposite sign. So what this is saying here is when you put in a negative number, you get out the opposite sign. Right? When you put in a negative, you get out a negative times a negative, which is a positive. Another way of writing this is saying that root x. Another way of writing this is saying that root x squared equals absolute value of x. Okay, that's an equivalence to. I'm telling you this because it's going to help us with a very tricky type of limit. It's the limit I ended with last time. Similar to the limit I ended with last time. So we'll find each limit. And we'll do the limit as x goes to infinity of root x squared plus 1 over x plus 1. But then we'll also do the limit as x goes to negative infinity of the same thing. So the kind of when you plug in infinity here, you're going to get infinity over infinity, right? Because if you square a big number and then square root it, you can kind of think of these canceling out and you just end up with the big number that you started with. Kind of, approximately, not actually. And if you plug in infinity on the bottom, well, that's just a big number plus 1, so still big. So this is an indeterminate form. You're learning to hate those, I hope. And kind of the strategy when you have an indeterminate form is to divide by the highest effective power. What's the highest effective power here?
X.
1, x to the 1. Right? Because this square root and this square at the end of the day, even though we can't simplify it exactly, it's approximately just x. So what I'm going to do is divide everything by x. And that's okay. That's legit. It's not a problem. Here, on the bottom, I'm not going to have any problem simplifying. The bottom is 1 plus 1 over x. How does the top simplify?
Get the x squared and shove it inside the line.
Now, you got to be a little careful here. You want to say, you would like to say that this is equal to square root of x squared, because then you can combine them since they're both under square roots. Is this equal to this? It depends on if x is positive or negative. If x is positive, they're equal. If x is negative, then actually you need negative x to make that substitution. But since I'm going to positive infinity, this is legit, this is okay. If I were going to negative infinity, which we'll do later, then I have x negative, and then I have to worry about something else. So this guy, we kind of make the assumption that x is positive since we're going to positive infinity. So then this is a true statement and everything works out okay. This becomes the square root of x squared over x squared plus 1 over x squared. Right? It just, this guy divides in underneath the square root. Go to positive 1, right? Because 1 over x squared goes to 0, 1 over x goes to 0, root 1 over 1 equals 1. So for this guy, it's still an indeterminate form because if you plug in negative infinity and square it, you get a huge number, and you square root it, it's still huge. If you plug in negative infinity down here, it's a huge negative number. So it's still an indeterminate form. Which means I still want to divide by the highest power, but now I want to take into consideration that x is negative. Right, that's what this is telling me. Kind of, what do you think I should divide by here? Think I should divide by x again?
1.
I'm going to divide by negative x. because that's going to make my substitution really easy. It's still a legit algebra move because I just divided top and bottom. But what it allows me to do is, since I have negative x, I can now replace negative x with square root of x squared. So on the top, because I know I'm dealing with negative x values, I know I can replace negative x with square root of x squared. So this guy is going to become square root of x. So altogether you get x squared over x squared plus 1 over x squared. So the top, if you look, ends up being the same, nothing happens. But the bottom, we have a sign change. The bottom is negative 1 minus 1 over x. So as x goes to negative infinity, this is 1, this is 0, this is negative 1, this is 0. So we end up with root 1 over negative 1. So this is tricky. There's nobody that's going to tell you this is not tricky. I don't particularly care a lot about this case, just because I know a lot of you won't understand it or remember it. Okay? But the reason that this is cool is because you actually have two different horizontal asymptotes for this function. All rational functions, polynomial over polynomial, have one horizontal asymptote if they have a horizontal asymptote at all. Like this function, for example, 2x squared plus 1 over 3x squared minus 4 has a horizontal asymptote at 2/3 ratio of the leading coefficients. But this function, it's not rational anymore because it has a root. But it has two separate horizontal asymptotes. On one side, it's approaching negative 1. On the other side, it's approaching positive. Whatever it does in the middle, we don't know too much about that. It's got two different horizontal asymptotes. So that's pretty cool. Questions? Is this going to be on the test? Maybe this one. I'll make it easy for you. I'll make it go to positive infinity. So you don't have to worry about this negative stuff. Compromise? Is that a compromise? No? Just so stop the questions real quick, but just so you know, there's one other thing they talk about in 1.5 and 3.5, and that's asymptotes. But since you've done that in 126 and 126 mainly, I don't want to spend a lot of time on it. But the last thing that I haven't mentioned at all about asymptotes. Saying, just so you understand the calculus definition of an asymptote, saying that if you say the limit as x goes to a constant from either the positive or negative of a function equals some kind of infinity. So if you do a limit from either side and you get infinity, that means you have a vertical asymptote. Okay, so this is the same thing as saying f has a vertical asymptote. Right? Because you're shooting off to infinity in the middle of your function. At some c value, here, say, you're shooting off to infinity, so you must have a vertical asymptote. Even if you only shoot off to infinity on one side, you still have a vertical. So a vertical asymptote is this behavior of shooting off to infinity in the middle of your graph. And it's described by this kind of limit. Right? This was an infinite limit. A horizontal asymptote is described by a limit at infinity. So this one was vertical. If you do the limit as x goes to plus or minus infinity, of a function, and you get out a finite value, this is a horizontal asymptote. This is the same thing as saying f has a horizontal asymptote.
Where?
At y equals f. So pictorially, we have a function that either as you go to positive or negative infinity, either one, your y values are approaching L. Oops. So you have this y equals L line. And your function's approaching it maybe on this. So a limit at infinity like this, equaling a finite number, gives you a horizontal asymptote. This limit gives you a vertical asymptote, but it doesn't really matter. Right, for all practical purposes, how do you find vertical asymptotes? Set the denominator equal to 0. That doesn't change, that's still the same. Because if your denominator equals 0, as long as you have a constant, right, to do this you look for c over 0. You need a constant over 0. That's how you get an infinite limit. So to find a vertical asymptote, you set the denominator to 0 after you simplify. So that's the same as always. To find a horizontal asymptote, your book went through last semester went through all this jazz about ratios of coefficients and blah, 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 blah. But you're just going to take the limit. Right? To find a horizontal asymptote, calculate the limit as x goes to plus or minus infinity. So let me do one example, and then I'll take questions. Find all vertical and horizontal asymptotes. F of x equals absolute value of 3x plus 2 divided by x plus 1.
So we simply just do the limit to infinite and then the infinite limit.
So for the horizontal asymptotes, you'll do the limit as x goes to positive and negative infinity. For the vertical asymptotes, you'll set the denominator equal to 0. So let's do our... First of all, you want to make sure nothing simplifies, because if it simplifies, then you have a hole and not a vertical asymptote. So I can't factor and simplify anything so that there's no holes here. So don't confuse a hole for a vertical asymptote. So try to simplify. But that doesn't work. So then we move on to vertical asymptotes, which we get by setting the denominator equal to 0. So if you set x plus 1 equal to 0, you get x equals negative 1. And if you check, if you were doing the limit as x goes to negative 1, you would get an infinity, right? You would get infinity on a different infinity on each side. Right? Because if you plug negative 1 back in, you get 0 on the bottom and a constant on top. Right? Negative 3 plus 2 is constant. That's negative 1. Absolute value is 1. So this does give you, just as a check, this does give you constant over 0. So you are going to infinity. So it is a vertical asymptote. But there's no need to check. I'm just wasting your time, I guess. As long as you don't have any holes, then if you get 0 in the denominator, it's going to be a vertical asymptote. The horizontal asymptote is the tricky part. For the horizontal asymptote, you're going to have to calculate two limits. The limit as x goes to infinity of your function, and the limit as x goes to infinity, a negative infinity of your function. Let me do that over here. So what's the limit as x goes to infinity of absolute value 3x plus 2 over x plus 1?
Infinity over infinity.
3.
3.
Yeah, so you got to be careful. You get infinity over infinity when you try to plug this in. So then you can divide by the highest power of x, but these absolute values make that kind of tricky. You guys know what this is? It's 3. Why?
Because when you plug in the highest exponent, you work everything
Yeah,
out.
so the highest exponents are both x's here, so if you look at the ratio of coefficients, it's 3. Right? But you have to worry about signs because the bottoms, because we're going to positive infinity, the bottom's going to be positive, so positive over positive is positive. Now, if we were being super technical about this, you would actually want to divide everything by the absolute value of x, but let me leave that a touchy-feely explanation for today. What changes when you go to negative infinity? So you still have the ratio of these coefficients, 3 over 1, but now since you're going to negative infinity, the bottom's going to a negative number. Right? The bottom's always going to be negative. The top's always going to be positive. So this guy here, x was positive, but this guy here, x is negative. So this is infinity over infinity. The bottom's negative, so you're going to go to negative.
So would you do the same thing we did with x, square root of x and divide by negative?
Yeah. So if you were going to do this out here, on the top one, you would do absolute value x plus 3x plus 2 over x plus 1, but you would divide everything by x. X, x, x. Since x is positive, this can slide right into the absolute value without a problem. So this will equal 3 plus 2 over x absolute value, 1 plus 1 over x, then you do your limit. On this guy, since x is negative, in order to make this x slide into the absolute value,
So give you absolute value.
you have to divide by negative x. This is one way to do it. Right, because now negative, x is already negative itself, so this is negative, negative, this whole quantity is positive. So you can put it in the absolute value without any problems. But then on the bottom you get negative 1 minus 1 over x, so you'll end up with a negative here. So when you do your limit, this guy will go to 3, this guy will go to negative 1. So your horizontal asymptotes, you have 2 of them here. Right, to answer the question, y equals 3, y equals negative.